Welcome to the Explainer. Today, we are pulling back the curtain on a really hidden fundamental challenge that's going on inside pretty much every piece of modern electronics. It's a problem that, if you get it wrong, leads to constant silent data corruption. Think about it like this. Imagine trying to pass a full bucket of water from one conveyor belt to another. The catch? Both belts are moving at completely different speeds and they're not synchronized at all. You're going to spill water everywhere, right? Well, in the digital world, that spilled water, that's your data, and it's gone for good. And that's exactly what makes this whole thing so terrifying. The source material for this explainer, a deep dive into digital design by Clifford Cummings, he really highlights that these aren't the kind of bugs that cause an obvious crash. No, these are the sneaky ones. They seem to work perfectly fine, like 99% of the time, only failing in these super rare, specific moments. And that makes them some of the most difficult and expensive bugs to ever hunt down. Okay, so let's really dive into the core of this. The issue is what engineers call asynchronous clock domains. So every digital part has a clock, kind of like its own internal heartbeat. Now, when two of these parts have different, totally unrelated heartbeats, they're living in separate clock domains. It's like having two drummers in the same band, but each one is playing to their own beat. It's chaos. To get them to work together, you need a special kind of messenger, a buffer called a FIFO, to safely pass the nodes between them. So this special buffer, this FIFO, it manages all the data flow using two pointers. You've got a write pointer that's always adding new data and a read pointer that's taking data out. These two are just constantly chasing each other around and around a circular memory buffer. The process itself is pretty simple, right? The write pointer fills up the buffer and the read pointer follows right behind it, emptying it out. This little dance works beautifully, keeps everything in order. Until we hit a huge paradoxical question. This creates a massive problem. I mean, think about it. Does this mean the read pointer finally caught up to the write pointer and the buffer is totally empty? Or has the write pointer lapped the read pointer and filled the entire thing up, meaning it's completely full? The pointers are in the exact same spot, but the meaning is the complete opposite. The solution is actually a pretty clever trick. Just add an extra bit that basically acts like a lap counter. So if the pointers are in the same spot with the same lap count, hey, the buffer's empty. But if the write pointer is a whole lap ahead, then it's full. It's a really neat solution to that paradox, but it accidentally introduces a much deeper, way more dangerous problem. Right, because here's where the real problem, the one that causes all those silent, nasty bugs, really begins. We have to read the value of one of those pointers from all the way across that asynchronous boundary. Remember, the two sides have their own heartbeats. Trying to read a number that's constantly changing from a different clock domain is just fundamentally unstable. And it turns out that standard binary numbers, the way computers normally count, can be incredibly unstable at just the wrong moment. Just look at this. The jump from the number 7 to 8 in binary. To go from 0, 1, 1, 1 to 1, 0, 0, 0, all 4 bits have to flip at the exact same instant. If our system happens to glance at the wrong nanosecond while that's happening, it might see a completely random garbage value and mistake a full buffer for an empty one. And that's a catastrophic data disaster just waiting to happen. As the source material says so bluntly, this multi-bit change problem is the core reason the simple approach is just doomed to fail. You just cannot safely read a standard binary counter across an asynchronous boundary. It's a recipe for disaster. So how do you solve this? Well, let's bring in the hero of our story. To solve this problem of all these bits changing at once, engineers turned to a really special way of counting. It's called a gray code, patented by a guy named Frank Gray way back in 1953. And its defining characteristic, its absolute superpower, is that to get from one number to the very next one, you only ever change one single bit. And this, right here, this illustrates the whole solution so perfectly. For that exact same transition from 7 to 8, the gray code only flips a single bit. This means our blurry photo problem, well, it's not a problem anymore. At worst, you might see the old value or the new one, but you will never, ever see garbage in between. The number is now inherently stable. So this is great, but how do we actually put this elegant one-bit trick into practice and build a system that's completely reliable? The whole process is actually pretty straightforward. One side counts using gray code. Then that value gets passed through a special circuit called a synchronizer, which is basically a little waiting room. It gives that single flipping bit a moment to settle down so it can be cleanly read by the other clock. And now, the other side has a completely stable, totally reliable copy of the pointer to check against. And with that stable pointer value, we can now use those simple rules we came up with earlier. By checking that extra lap counter bit, the logic becomes crystal clear. If the lap counters are the same, it's empty. If the right side's lap counter is one ahead, it's full. No more ambiguity, no more corruption. Problem solved. But hold on, there is one final, kind of counterintuitive twist in this whole design that makes it truly robust. It's this idea where being a little bit slow is actually a feature, not a bug. So when the buffer is about to get full or has just become empty, the system raises a flag immediately. The instant the right side thinks it's about to overflow, it screams, "Stop, I'm full!" That makes perfect sense, right? You want to prevent an error. But here's the weird part. After the read side grabs an item and frees up a spot, the right side doesn't immediately get the all-clear signal. No, it's intentionally held back for a few extra heartbeats. This deliberate delay is what engineers call a pessimistic design. And the reason for the delay is pretty simple, actually. It takes time for the news that the read pointer has moved to travel safely across that clock domain boundary and get synchronized. The system basically waits a couple of extra clock cycles just to be absolutely 100% sure that the "hey, a space is free" message has been received correctly. And ultimately, that's what this all comes down to. In high-speed digital design, absolute data integrity is everything. This pessimistic delay is a tiny little safety margin that guarantees the system never, ever makes a mistake. Pausing for an extra nanosecond is infinitely better than corrupting data, because preventing disaster is always more important than raw speed. This whole elegant dance of pointers and gray codes and these pessimistic delays, it's just one of thousands of hidden engineering feats that make our complex digital world even possible. It's a perfect example of a clever, super robust solution to a problem most of us never even knew existed, working silently right now to protect our data every single day.